Next theorem is Rouche theorem. The statement of the theorem is if a function f of z and g of z are analytic inside the, if these of all of these function are fz and gz, these are analytic inside the simple closed contour C, and if modulus of g of z is less than modulus of and fz plus gz has same number of 0 inside the C. So remember that if all these conditions are satisfied, then the function fz and fz plus gz has same number of zeros inside C. It means same number of 0 means same number of roots. So this is the statement of the Rouche theorem. Now in the given part, the function fz and gz are analytic within and on a C, and modulus of gz is less than modulus of fz on C. Then step number 1, neither fz nor fz plus gz has 0 on C. Now since what is the given part, f of z and g of z, these both are analytic within and on a closed contour C. This is one condition. Second condition is modulus of gz less than modulus of fz, which is on the closed contour C. So this is a, suppose this is the equation number 1. Now that is a given part. My aim is to prove that fz and fz plus gz has same 0 inside C. So we will prove it by contradiction. The step number 1. So this is step number 1. So what is the step number 1? So step number 1 is neither function fz nor fz plus gz has 0 on C, has 0 on C. It means first I want to prove that the function fz and fz plus gz has no 0 on C, not inside, on C. So that is my first step to prove the result, because I want to prove that it has all the 0 inside C. So first I would like to prove that neither fz and fz plus gz has any 0 on the C. Now if suppose f of z, if f of z has 0 means root on closed contour C, suppose also we know that modulus of gz is less than modulus of fz, this is on C, so that is given part. Then it implies if fz has 0 on C, so suppose A is the 0 of the function, then it means f of A at the point A, it has the root, so it means f of A is equal to 0. By using this concept, we get modulus of g of A less than modulus of f of A. So this value, so what is this? It is a 0. So it implies modulus of g of a is equal to 0. So it implies g of a is equal to 0. So g of a equal to 0. So it implies both have the same value, which is a contradiction. So it implies f of a and g of a are equal. But in the given part, they are not equal. G of z is less than c. So this is contrary. So this is contrary to the assumption, contrary to the assumption number 1. Assumption 1. So what is that assumption? That was modulus of gz is less than modulus of fz, this values. So this is assumption on 1 on C. So by this assumption. Now again, if fz has, it is, we take about the function fz. Now I am taking the function fz plus gz. So if the sum of the function f of z plus g of z, so this is a sum of function, has 0, has 0, that 0 say it is a on C, then it implies f of a plus g of a, which is equal to 0. So what we get? We get f of a, which is equal to minus g of a. So again we get modulus of f of a, which is equal to modulus of g of a, these values. Again, which is contradiction. Why it is contradiction? So again it leads to contradiction. It leads to contradiction by equation number 1, right? Because in that case it is less than this. So what we get? We get fz, we get f of z, one function, and f of z plus g of z. Both the function has no 0, has no 0 on C. So that is my first part. That is my first step. Ki they have no 0 on C. If they have 0, then they must be inside the C. Now step number 2. So step number 2. So now I am taking the step number 2. So what is step number 2? Suppose, let, what is n1? So n1 is number of zeros of fz inside C, and what is n2? n2 is the number of 0 of fz plus gz inside C. So I am taking n1 and n2. So inside also we can use it as within. So it leads to what we get by previous result. It leads to 1 by 2 pi iota integration around C f dash z over f of z into dz, which is equal to number of 0 minus number of 0. So this is n1 minus number of pole, which is a 0. So this value is equal to n1. So this is written as equation number 2. So this is from first part, from n1. Second, the function is fz plus gz. So in that case, this will become 2 pi iota integration around c. So what is f dash z plus g dash z over f of z plus g of z into dz, which is equal to n2 minus number of pole, which is 0. So this is again n2. So I write it as equation number 3. So by using that result, I get the value of n1 and n2 in term of integrations. Now, subtracting equation number 2 from equation number 3, so what we get? We get subtracting equation number 2 from equation number 3, we get. So first subtract, then what we get? We get, so this is f dash plus this values. So this is a 1 by 2 pi iota. So which is a common part, integration around c, bracket f dash plus g dash over f plus g minus f dash over g dash, sorry, f dash over f. So I write it again. So 2 so here this is a f into dz, so which is equal to, so first is a n2 and second is a n1. So this is a n2 minus a n1. So this is equation number 4. So this is the equation number 4. We get these values. Now, if I take g of f, which is equal to a function phi. If I take g of f is equal to function phi, then it implies g function is phi into f into phi. Now, since we know that modulus of g is less than modulus of f, it implies modulus of g by f, which is less than 1. This values, modulus of g by f less than 1. So what we get? We get from this modulus of phi, which is less than 1. So which is equation number 5. So here we write the function phi, modulus of phi, which is a less than 1. Now, also we know that what is the f dash plus g dash over f plus g. So simply substitute the value of g. So what we get? We get f dash plus phi into f dash over f plus phi f. Now what is the next step. So f dash, now integrating phi into f dash plus phi dash into f over, if f is common, then 1 plus phi into f. So what we get? We get 1 plus phi into f dash plus phi dash into f over 1 plus phi into f. So just simplify. So simplify this equation. So we get this values. Now we get this values. Now from the first part, from this, if we divide this term, from the first part we get f dash over f, and from the second part this f is cancelled, so which is a phi dash over 1 plus phi. So we write this value in this form, this values in this form. So what we get, this value is equal to this values. So it means f dash, it implies f dash plus g dash over f plus g minus f dash over f, this value, and this value is equal to phi dash over 1 plus phi, this values. So when we take the this values, so we get this values. Now if I take the integration around c, this function, and this is with respect to dz, and again this is c function with respect to dz. Now multiply by 1 by 2 pi iota, here 1 by 2 pi iota into integration of phi dash over 1 plus phi. Now substitute its value. So what its value? So its value is equal to n2 minus n1. Now substitute this value. So this is n2 minus n1, and what is this value? This value is integration around c. So phi dash, which values? Into 1 plus phi raised to power minus 1, it is a function of z, into d of z. So this value here we write in this way. Now this right hand side, so it is by, since phi is less than 1, so I write it in the form of binomial expansion, so which is equal to integration c, what is this, which is a phi dash into bracket, so this is by binomial expansion 1 minus phi plus phi square minus phi cube plus so on up to infinity into d of z. So why it is possible? It is possible since modulus of phi is less than 1. So that is a modulus of phi less than 1. If modulus of phi is less than 1, and also here 1 by 2 pi iota. Also here 1 by 2 pi iota. So remember it. Now this, if taking the integration around this, so what we get? We get 1 by 2 pi iota integration around c bracket. So this is a phi dash, this is phi dash minus phi dash into phi. So this is a derivative and this phi. Again, this so we also write it as a individual term. So this is, we can also write it as individual term. So what is the individual term? So individual term is of this kind. Now individual term, I write it as a individual term. So phi dash z and so on. So what we get? So we get the term. So this is a phi dash minus phi dash z plus next term, which is plus phi square into phi dash into dz and so on up to minus and so on up to this, and this is a derivative dz. Now this can be written as individual term. So individual term means this is equal to 1 by 2 pi iota bracket this. So what is this? This is the integration c phi dash into dz. First term minus second term, which is c phi into phi dash into dz, and third term, which is equal to integration c phi into phi square phi dash into dz minus so on up to infinity. So this term. Now this term, when we add all this term, now since fz and gz are analytic within and on the C, then it implies phi z and all its derivative are analytic within and on the C. So since f of z, since f of z and g of z, these are all, these are analytic, these are analytic within and on a simple closed contour C, then it implies the function phi z is also analytic, also analytic within and on a closed contour, contour C, contour C. Now apply the Cauchy-Gauss theorem. So this term, this integration is 0. This integration is 0. So 1 by 2 pi iota bracket 0 minus 0 plus 0 and so on up to 0. So this is equal to 0. Now phi z is analytic. Phi z and all its derivative. Phi z and all its derivatives are analytic within and on a simple closed contour. If they are analytic, then integration around that is equal to 0. If integration around that is equal to 0, so it implies n2 minus n1 equal to 0. So what we get? We get n1 is equal to n2. So what is n1? n1 is the number of 0 of function fz, which is equal to number of 0 of function fz plus gz. So it implies function fz and fz plus g of z has same number of 0 0 inside ja within C or within C. So this is a proof of the Rouche theorems that these functions did not have any root, any zero on C. If they have zero, they are inside C, and fz and fz plus gz, these have the same zero inside the C. Now, for example, in order to discuss the Rouche theorem, application of Rouche theorem. Now consider a function. So I consider a function which is equal to z raised to power 6 minus 5 z raised to power 4 and plus 7, and this is modulus of z less than 1. So this value is modulus of z less than 1. So this values. Now I consider z raised to power 6 and minus 5 4. This is equal to gz function, and this fz I am taking as a constant 7. And what is gz? So I am taking gz, which is equal to z raised to power 6 minus 5 z raised to power 4. This values. Now what is modulus of gz over f of z? So just substitute its value. So what we get? We get modulus of z raised to power 6 minus 5 z raised to power 4 over 7 by using this is less than equal to 1 by 7, that is bracket modulus of z raised to power 6 plus 5 and modulus of z raised to power 4. Since modulus of z is less than 1, so this value is less than 1 by 7 bracket 1 plus 5. So this is a 6 by 7. So this 6 by 7 is less than 1. It means what we get? We get modulus of gz is less than modulus of gz is less than modulus of fz on modulus of on a circle with modulus less than 1, on a circle with radius less than 1. Now both the function fz and gz are analytic, so these are polynomial, these are constant. If both the function of analytic, then by Rouche theorem, it satisfy all the condition of Rouche theorems. So by Rouche theorem, the function fz and fz plus gz, they have same number of 0 0 inside modulus of z less than 1. Now fz is a constant, so it has no 0. Gz has, this is of this kind. It means it has no 0 inside C. Then the given function has, then it implies the given function z raised to power 6, z raised to power 6 minus 5 raised 5z raised to power 4 plus 7 has no zero inside the circle modulus of z less than equal to 1. So this is very important result. So we see that this polynomial has 6 roots, but I want to find out how many roots in this circle of radius 1. So what I get, it has no root in the circle of radius less than 1. If this is the origin and radius is 1, so it has no root inside it. So by fundamental theorem of algebra, it has 6 root, but it has no root, no zero inside the circle of radius 1. So this is a application of Rouche theorem. So in this way, we can find the number of zero of any polynomial, any values, so that it has how many zero inside the circle or not. So there are lot of example we will discuss in the next lecture. So now in the next lecture we will discuss the fundamental theorem of algebra.